history of the Sanford Underground Research Facility. It's located in Leeds, South Dakota, and it's the site of the former Homestake Gold Mine. The first physics experiment was conducted by Ray Davis in 1960s, and what he was studying was the solar neutrinos. And what makes the location of the mine so good is that it's deep underground. Some places are almost a mile underground, and that shields it from like solar radiation and other forms of radiation from space. Oh, and the mine was closed down in 2001. The site was donated in 2006, and then Denny Sanford contributed $70 million to make it a research facility. And the most famous experiment, the Large Underground Xenon experiment, started in 2013. The Long Baseline Neutrino Facility and the Deep Underground Neutrino Experiment is a collaboration with Fermilab in Illinois. It studies neutrino behavior and how they change over long distances. The neutrinos are sent from Batavia, Illinois to the Sanford Underground Research Facility, which is a distance of about 800 miles. The detector in the Homestake mine will open up in 2021. The Majorana demonstrator is a small-scale model of a neutrino experiment that will determine whether it's feasible to get a certain amount of radioactivity deep in the mine, and they're trying to get it lower so that there's less background noise. And the full-scale experiment would attempt to determine if neutrino is a Majorana particle, which means it's its own antiparticle. And the way they would do that is determining if there's such a thing as neutrino-less double beta decay, which is basically just a certain kind of radioactive decay where 2 electrons are emitted without a neutrino. And this demonstrator came online in 2015. The Large Underground Xenon experiment is easily the most famous of the Sanford Underground Research Facility experiments. It's searching for dark matter, and it's using 370 kilograms of liquid xenon inside a 70,000-gallon water tank. The water tank is to eliminate even further the background radiation, and then the xenon is used to detect the dark matter. They're searching for the interactions between dark matter and xenon. Basically, when a dark matter particle might directly interact with a xenon particle, it would emit a photon, and they have very sensitive detectors in there that would detect the photons. They've had 2 test runs so far, 80 days and 300 days. The most recent one ended in late 2016, and they have found no positive results for dark matter so far. But the Lux Zeppelin experiment, which should be about 100 times more sensitive, will come online in 2020. Any questions?
So I remember last year that School of Mines featured something with this lab. I remember the one picture that you had coming from Fermilab to this facility. Do you know what the School of Mines has to do with this project?
They're very, the physics department is very interactive with this experiment, I guess. They get a lot of the information from the lab and basically kind of interpret it, and they can write papers on it and whatnot. So there's a lot of interaction between the two.
Do you recommend that this is something ICPC goes and sees?
Yeah, they have, you can't actually go inside the mine, but they have tours of the surface campus, which has a couple of different buildings where they do research and stuff. And you can get a tour of the mine shaft, where they take the elevator down, and then they also offer tours of Leeds, South Dakota.
If you look at the bottom line, why is this so important?
Basically, in terms of dark matter and neutrino research, this is the top tier of research.
In the world?
Yeah, and like dark matter research is one of the biggest questions in physics right now, so it's very leading edge, cutting edge.
What is dark matter?
So we don't really know yet. Basically, galaxies rotate a little faster than we would expect without dark matter, and so the only way that they can make it work is if they add in mass somewhere, which would come from dark matter. And the the leading idea is that they are weakly interacting massive particles similar to neutrinos, and basically that means they only interact through gravity and the weak force, which is very complex. I won't get into that. But yeah, basically the only way to detect them is through their gravity and through their direct interactions with particles.
Right.
That's pretty good, that was kind of an